Good afternoon, everyone, and welcome back to the second session on hands-on session on quantum communication. So, in the previous session prior to this, we had our external speaker, Mr. Rikin Baumik from Quantum AI Global, who gave us an introduction to the general idea of quantum communication and why we need to shift from classical communication systems to quantum communication systems. What are the benefits? What are the resources that we are going to use? And different algorithms. So today we'll try to continue on the same path. So what I'll do is first I'll try to show you one example of Shor's algorithm, and I'll show you that uh, although Shor's algorithm promises to break the cryptographic system, that promise is far from realized, and it'll take us many years to achieve that promise. Then I'll show you two protocols using the something that quantum has and the classical does not, which is the property of entanglement, and how we can utilize it to our advantage. As the theory for the same has already been discussed by Mr. Rikin Bhomik. Then the main part will be to using quantum, how one can generate cryptographic keys. So that will be the main focus, and we'll end over there. And then, yeah, again, as I had mentioned in the mail, that this is an interactive session. So I would really like you guys to interact with me as much as possible so that we can both understand and gain something out of it. Right. So with that, let's get started. I'll share my screen again. Okay. So I hope my screen is visible. Right. So classical communication and RSA encryption. So as we have already heard from Mr. Rikin Bomit, that whatever the communication or whatever the cryptographic system that we have, these are currently based on the RSA encryption. Although he also showed you some different encryption methods which are not, in threat due to quantum, but this RSA encryption is, and that is due to uh, the algorithm of Shor's, which shows that you can factorize two prime numbers. You can factorize given prime number, and that is basically the basis based on which this RSA encryption is done. So Shor's algorithm is a bit complex to understand at this level because it involves certain concepts like phase inversion, quantum Fourier transform, inverse quantum Fourier transform, and on top of that, you also need the knowledge of RSA encryption system. And so I'll not go into the detail of the Shor's algorithm as to how the Shor's algorithm is being designed. Rather, I'll just directly show you the result, and I'll also show you why this is not yet a threat at this moment of time due to the noisy quantum system that we have. But later we'll share this IITY notebook with you, and you can try it by yourself, and perhaps you can try to optimize this code as well, because the code that I'm going to show you, it's not that optimized code. So here you see that I'm trying to factor 165. So 165 is my number, and I need to find two factors of 165. Now, if I run this over here, I can very well do that, but that will take some time. So I have already run it previously. And you see that it has factored it into the two primes, that is 3 and 15. And if you are a bit familiar with this, then you'll already see that this is not the the optimal factorization, because we try to avoid the smaller prime factors as much as we can while we are encrypting using RSA. So this is obviously not the correct answer, and that is why I said that perhaps one of you can try to optimize this algorithm, because this is not optimized. Now you see that for 165 factor, it took 25.4 seconds. But if I do this, if I try to do the same for the factor of 299, then it will take more than that. I'll let it run in the background. Before that, I want to show you something. Uh, so basically, what I wanted to show you is the quantum circuit needed uh, to factor the 165, and you will see that the quantum circuit becomes very big. As far as I remember, this 165 factorization only requires 21 qubits, and that is a very high number of qubits. And not only 25 qubits, but sorry, not only 21 qubits, but the gates that are being applied on the qubit. So the number of gates is also very long. And since due to the very high factor of noise in current quantum systems, this becomes practically unfeasible. And this is just for a small number like 165. Currently in cryptographic system, we are using very large numbers, so Shor's algorithm is not a threat as of now, as you might have heard from someone. So we'll let it run, and we'll go back to our slide. We'll come back to it later. But now I wanted to discuss a few, not a few, I mean, couple of protocols using the workhorse of quantum information processing, if you will, that is the quantum entanglement. And using quantum entanglement, you can basically perform the teleportation. Those who have watched Star Trek might know what the teleportation is. And the second is Superdense Coding. I'll explain you both in detail as well. But before that, just a recap. So we represent any general state of the qubit as alpha 0 plus beta 1, and alpha and beta are just complex number. The only requirement, or only the constraint on the alpha and beta, is that mod alpha square plus mod beta square has to be 1. Apart from that, alpha and beta can be any complex number possible. Then different quantum gates. So we have a Hadamard gate, which creates an equal superposition. So when Hadamard gate is being applied on the state 0, it becomes get 0 plus 1. And this is also known as the plus state. And when X gate is applied on 0, it flips the qubit. Z gate is phase, so it applies a phase. And C note is the gate that we used for the entangling the qubits. And we have already seen that these four are the entangled state, or also known as the build state, because if you see that, see, this is 0, 0 plus 1, 1. So if I know the state of the first qubit, I immediately know that since my first qubit is 0, second has to be 0. And if my first qubit is 1, then the second has to be 1. And same logic can be applied to rest of the three states. And using these entangled state, one can realize a protocol known as the superdense coding. So the general idea of the protocol is this. There is one person known as the Charlie who prepares the two entangled qubits. It could be any of these four state, but let's just say for the moment that he prepares this 5 plus state, which is 0, 0 plus 1, 1. So since two qubits are prepared, which are entangled, this Charlie sends one qubit to Alice and sends the other qubit to Bob. Now the task for Alice is to send a classical message to Bob. That classical message is a 2-bit message. And since it's a 2-bit, it can be 0, 0, 0, 1, 1, 0, or 1, 1. So Using the classical systems, we can easily understand that in order to send this 0 and 1, assuming that Alice wants to send 0 and 1, she needs to first send 0 and then she needs to send 1. So it's in a way a 2 bit of information that she needs to send to Bob. This is the classical scenario. Now the quantum scenario is that we are claiming that using this entangled state, we just need to transfer the quantum bit just once. So in classical, you need to transform these 2 bits in order to transmit the entire message, while in quantum, you need to transfer just 1 bit. And as I said initially, so 2 bits are prepared. 1 bit is given to Alice, the second bit is given to Bob. The, the bit that Alice has, she will send that bit to Bob, and just 1 bit of transformation, we are able to send 2 bit of information. And this is obviously the reason why it is called super dense coding, because in order to send 2 bit of classical information, we are just transmitting 1 bit of quantum information. And the way this protocol works is very simple and very easy to understand. Is that Assume that if the intended message is 00, then Alice will apply a particular gate onto her qubit. Since we have already seen that the message is 01, so the message is 01, and so the Alice will apply X gate. And by the way, this information table is with Alice as well as with Bob. So both are aware of this encoding, which is that if Alice wants to send 00, then she will apply I gate to her qubit. If she wants to send 01, then she will apply X gate to her qubit only. If she wants to send 10, then she will apply Z gate to her qubit only. And if she wants to apply 11, then she will apply Z gate and X gate to her qubit only. I'm repeatedly emphasizing the fact that Alice is doing the operations on her qubit only, and that is very important because uh, until this point onwards, Bob is doing nothing. He's just sitting idle and waiting for something to receive from Alice. So whatever is being done at the Alice's end, and nothing is done at the Bob's end. So now assume that she wants to send 01, then she will apply X gate onto her qubit. And since our initial state was this 00 plus 11, so X on the first qubit will turn 0 to 1, and the X on the second qubit will also turn 1 to 0. So this is the state which is shared between Alice and Bob. Now what Bob needs to do is he needs to so now what Alice will do is Alice will send her qubit to Bob. So this is what has happened so far. Third party, it can be Charlie. Let's call it a Charlie. So Charlie prepares 2 qubits which are entangled with each other. Charlie sends 1 qubit to Alice, 1 qubit to Bob. Alice wants to send 01 to the Bob, but instead of sending this classically, she chooses to use quantum and to send 01 according to these encoding table. She needs to apply X gate on her qubit. She does that. Then she shares her qubit to Bob. So now Bob has access to 2 qubit. As you can see, this is the qubit which was shared by the Charlie initially, and this is the qubit which is shared by the Alice. So Bob now has 2 qubits at his disposal. Now what Bob will do, Bob will simply perform the Bell basis measurement. If you don't know what Bell basis measurement is, that's fine. You can just consider it as a measurement. If Bob, and since we have already seen that this is the state which is shared between Alice and Bob, that is 10 plus 01 and 10 plus 01. So if Bob performs the Bell basis measurement, then what he will receive is 01 at the end. The Bell basis measurement is nothing but first he will apply the C0 gate with the qubit that he has received from Alice being the control, and the qubit that he has received from Charlie being the target. And then he will apply Hadamard gate on the qubit that he has received from Alice, and then he will measure both the bits into the computational basis, and he will get two results which can be 00, 01, 10, and 11. Now, this result will depend entirely on what is the gate that Alice has applied. So, if Alice has applied X gate, then the output will be 01. If Alice has applied identity gate, then the output will be 00. Similarly, the for combination and for the inputs applied gate by the Alice. And by looking at the result that Bob has got, you'll be able to understand that Alice wanted to communicate classical bits 0 and 1. This is the simple protocol in a nutshell. Now let us see how that is being implemented in Qiskit. And again, since as Rikin rightly mentioned in the previous talk, that quantum processors are very localized processors. So this is just a demonstration of how Superdense coding protocol works, but it's practically not of any use if you are using superconducting hardware. It can be used when you are using photonics hardware because then the two parties will be separated by a large distance. While in this case, using Qiskit, the IBM superconducting hardware is not that separated with a distance. But just to see that if the superdense coding protocol works or not, we can do that. So what I'm doing is I'm just simply creating one entangled circuit between Alice and Bob. Uh, and this is this will create 0 and 1. Then I'm encoding the message. So if message is 00011011, then based on that, I'll be applying identity, X gate, Z gate, and XZ gate. So this function will do that. Then I'm decoding the message. So at the part of the decoder, all Bob needs to do is apply CX gate, basically the CMOD gate and the Hadamard gate. This combined, this two measurement is known as the bell basis measurement. And then we put all this together. Now suppose we want to send message 10, then this is what the circuit. Okay, quantum circuit is not defined. I've done something. Yeah, I have forgotten to import all the required libraries. I'm sorry for that. Okay, now it should work. And it does. So this is the circuit. You see that first the entangled state is prepared. Then based on the qubit that Alice wants to send, she will perform some measure, she'll apply some gate, and then the bell basis measurement is done, and then the Z basis measurement is done. And if you visualize the measurement result, we got the bit 10 as a result. And this was indeed the message that Alice wanted to send. So yeah, superdense coding works. Here you will see this 1024. So just to make sure that whatever we have done is working perfectly, we'll be repeating this experiment 1024 times. You can change this to as many number as you want. It's generally a good idea to go as high as you can so that you get a very good measurement statistics. Right, once we are done with the superdense coding, then the second part is the quantum teleportation. And quantum teleportation is not just a superficial idea anymore. It's practically possible. However, as we have seen in movies or somewhere, that it's not an instantaneous transfer. It does follow certain rules imposed by the theory of relativity, that no communication can take faster than the speed of light, and this protocol also follows that fact. So the simple illustration is shown over here. So, So simple illustration is shown over here. So again, here Alice and Bob will share an entangled qubit. So one entangled qubit is given to Alice, the other entangled qubit is given to Bob. Alice will perform some operation on her qubit, then she will do the measurement. That measurement result will be the classical result, and that classical bits can be shared to Bob. Based on this received classical bit, Bob will perform some measurement and he will have what Alice wanted to send. So the biggest difference between superdense coding and the teleportation protocol is that in superdense coding, Alice is sharing her qubit to the Bob, while in teleportation, Alice is sharing her classical bits with the Bob. That's the general idea. So the process will be Alice will prepare some random state, and the thing that is being teleported, the information that is being teleported is the information about any random quantum state. And those who are a bit familiar with quantum computing, they might be aware of the fact that you cannot clone any unknown quantum state. So in classical, we just simply do control C plus control V. In quantum, you cannot do that, given that your state is unknown. And so this is where this protocol comes in, because if Alice wants to send this unknown state to Bob, then she will has to resort to this particular protocol. And the way it works is, so this will be the circuit for the teleportation. So what is happening simply is, so the qubit 1 is with Alice, qubit 2 is with Bob, and qubit 0 is the state that we wish to teleport from Alice to Bob. So now what is happening is, focus, my cursor is visible. Yeah, so focus over here. So you see that this particular part of the circuit is creating the entangled state shared between Alice and Bob. The next part, the Alice and the unknown state. So whatever the operation is being done here is happening between the Alice and the unknown state. So what is happening is, since Alice is doing something, the unknown state is being teleported to the Bob's qubit. Then Alice performs the measurement, and since the measurement is done, whatever the state was here with the unknown state and with Alice's qubit is collapsed, and all the information of this unknown state is being transferred to Q2, and the information can be retrieved by the means of the measurement, and this measurement is again conditional measurement. So it is something like what we have seen. I think I have that. No, I don't think. So this teleportation is also something like what we have seen over here. So since there was a one-to-one correspondence over here, similarly, there will be one-to-one correspondence on the measurement of the state. Right. So if you see that the state that she wanted to send, the state that Alice wanted to send is nothing but the plus state, or the uh, superposition state of 0 and 1, an equal superposition state rather of 0 and 1, because if you start with a gate 0 and then you apply Hadamard gate, what you will have is 0 plus 1. So that particular state she wanted to send, and at the end of the teleportation protocol, if I print the individual state of the qubit, then you see that at the end of the protocol, qubit 2 belongs to Bob, and that qubit is in the plus state, which is what we would expect, given that the teleportation protocol works. And that is what we also see. This is also one proof that, yeah, indeed, teleportation protocol works, and it works very well. Now, all the protocol that I've shown you, namely the superdense coding and teleportation, these were executed on air simulator in this particular notebook, but you can try to simulate these protocols into the actual hardware, or maybe using noisy hardware, noisy simulator as well. And there you will be able to see the effect of noise. And there also you'll be able to see that why current quantum computers are not that useful. Okay, I see this is still running, so we'll let it do that. Right. So now let us move towards the cryptographic algorithms. Those are three algorithms. It should be E91 or BB91. Sorry. So although I have mentioned two protocols, I will not be going into the detail of each one. I'll just show you that how keys can be generated using these algorithms. Then once the key is generated, then the process is similar to what we have in classical cryptographic system. The key is shared between the receiver and sender party, and through these keys, one can decipher the message. So first, we'll start with the BB84 protocol. So the name comes from the fact that it was proposed by these two gentlemen, Charles Bennett and Gilles Bresard. So B and B comes from here, and it was proposed in 84. So BB84. Similarly, E91 comes from the fact that it was proposed by a gentleman named Arthur Eckhart, and it was proposed in 91, so E91. And B92 is similarly proposed by Charles Bennett in 1992, so B92. And Ritim explained the workings of the BB84 protocol, so I'll not go into that in very detail, but in just a vaguely manner, you can understand that uh, Alice prepares random, basically she prepares a qubit and measures in a random basis. These random bases could be 0, 1, plus or minus being the rectilinear or the diagonal basis. Then sends her qubit to Bob. Bob will measure the qubit in any randomly chosen basis. Once the entire process is done, and they will be repeating this process n times. Once that is done, then they will publicly announce that Alice has measured in this many bases and Bob has measured in this many bases, and then they will compare. When the bases match, that will be the key. So I'll randomly select basis for Alice. I'll randomly select basis for Bob. For the moment, I'm restricting myself to Z and X, and we are using 20 qubits. You can go higher as well, but for this purpose, I'll be using 20 qubits. So I have got Alice's basis. I have got Bob's basis. Let me print those as well. So this will be the Alice's basis. You can see that it is completely random, and I can do that again, and you see that it is random. So first you'll prepare in X, then Z, then X, and similarly Bob will do the same. And let me print the Bob's basis as well. So Bob's bases are also random. It could be anything. Now, what we'll do is, as it's in here that she will encode a bit into the chosen basis. So what that will basically do is, she will, let's say, first chosen basis is X, then she will prepare her qubit in 0, then apply X gate, then they will share, then she will send that qubit to Bob. Now, if Bob also receives the now if Bob also randomly applies the X gate, then whatever the initial state was there, same will be received by the Bob. Let me show you an illustration, and that will be easier than. Okay, so what is happening is, so Alice is starting with, let's say, gate 0. Then she will randomly choose any basis from this set. Let's say she chooses X, so she will apply X on her qubit like this. She will send to Bob. So this is Alice's power. And now this is with Bob. Now Bob also has two choices, X and Z. Let's say for the simplicity that Bob also chooses X and this is completely random. Then if Bob also applies X on the state received from Alice, then you can see that this X is nothing but, sorry, not unitary, it becomes identity. So the 0 remains 0, and when Bob does the measurement, he will get the result as 0. Now, what if the other case happens? Alice is sending again X, and Bob is applying Z and 0. Then Z on 0 will again be uh, sorry 0. But if instead of Z, Bob applies X, uh, yeah, any X or Z, then you can see that there will be some, some result will be obtained. And what happens now is, yeah, they will basically compare that whatever the result that I've gotten, I mean, how many of result that I've gotten is same, and how many of the result that basically they'll complain. Basically they will compare the basis. So if Alice has also chosen the same basis as the Bob, then they will have the same results. Otherwise, they will have the different results. And you can see just either click on this. As you can see, on the qubit 0, basis matches because Alice also choose X, Bob also choose X, and Alice's bit was 1. So the key would be, the first bit of the key would be 0. In the second case, there is a mismatch. So whatever this result, we will discard this result. Since there is also a mismatch, we'll discard this result as well. We'll also only consider the results where this basis is matching, and this will be the final key that we will get. And this is the key that Alice has as well as Bob has. And now both parties have the key shared between them. There is no need to share the key over a classical communication channel or any type of channel where there is a possibility of eavesdropping. And since the no communication is required, it is in theory guaranteed that this key is a very safe key to use for the cryptographic purposes. This was one protocol. Now, if we assume that somehow there is somehow someone is able to intercept the qubit when Alice is sending the qubit to Bob, then there is a problem. So let's do that as well. So what happens is, again, we are doing the same thing. So Alice randomly chooses her basis, and now we are assuming that there is an interception. So eavesdropper is there, and when Alice is sending her qubit to Bob, eavesdropper will correct that qubit, will perform some measurement, and then she will again prepare a qubit of herself, and then they will then she will send the that then she will send that particular qubit to Bob, and Bob will again do the measurement. Then how will Bob and Alice know that there was an eavesdropper in the channel and that eavesdropper has got the access of our information? It is very easy to see. So the way it works is they will take a sample, not the entire key, but the key of with the sample of the key distribution. And you see that the key for the sample from the Bob and sample from the Alice are exactly the same apart from some places, as you can see. And this is the indication of the fact that there was someone in between who has interfered with the communication, because if you see that when the basis for the Alice's encoding and the Bob's encoding are the same, then by quantum mechanics it is guaranteed that they should have the same digit for they should have the same digit. So here they have the same digit because their basis was matching and there was no use in between. But here that is not the case. So the fact that the bases are same, but the chosen key bit is not the same shows that there was an eavesdropper. And if you see the theoretical analysis, uh, then you can show that if your based on the size of your key, if if number of bits that are mismatched are higher than a certain threshold, then you can say with certainty that there was someone who was in between Alice and Bob's communication channel and have access to a particular key that was being shared between Alice and Bob. So they will Bob and Alice will discard that particular key and then they will start the process all over again. This was just a small demonstration of how this thing would work in actual practice. And if you are interested, you can explore this further in detail, and we'll share some guides with you as well if you are interested. So I'll not go into detail of the E91 protocol. I'll just briefly discuss the B92 protocol. The main difference between the B92 protocol and BB84 protocol is that in BB84 protocol, we are not using any entanglement. We are just relying on the fact that qubit, when measured in same system twice, will remain the same as when measured in same basis twice, or the when encoded in same basis twice will remain the same. While if the basis change or the encoding change, then the state of the qubit will change as well. So that particular property comes from the superposition property of the quantum mechanics. But if we wish to use the entanglement property as well, then this protocol can be utilized. This also is very simple protocol, and the implementation of the protocol is also the same. Alice and Bob randomly chooses basis to measure that particular qubit into. Then they will exchange the qubit. Then they will publicly announce that, yeah, Bob has measured in this many bases. Alice has encoded in this many bases, and whenever the basis is matched, then they have got the key. So in this case, Bob's result is something like this. And again, this is the entirely completely result. You will not get the same thing twice. And when they compare, then they will only consider the bits where their basis is matched. So this is the key for the Alice, this is the key for the Bob, and you can see that these are the access exactly the same. So using this key, now they can do the encryption. And I've shown the example of encryption as well using this generated key, and you can see that the encryption is successful. And if I do this again, I need to change the key. So now since the key is changed, you will see that encrypted message is also changed. Let me show that again. So the Bob's result is changed. So see the result is changed. So due to this, the key should also change. And due to this change in the key, the encryption should also change, and it does. So this is again a very very general and a very brief end-to-end overview of how the key distribution systems using quantum will work. Now there are several different possibilities of attacks, and people usually go into the detail of how many ways using which the eavesdropper can try to intercept the communication between Alice and Bob. And based on the different kind of possibilities using which, or based on the different kind of scenarios through which Eve can attack communication between Alice and Bob, people have developed several quantum cryptographic system where certain systems are guaranteed to be safe even if the eavesdropper is in there in the channel and is trying to detect something. Or there are several other protocols which will give you the clear cut indication that there is something wrong with the channel and you should discard this particular key and start a new one, or maybe verify the channel or do something else with the channel. So this was a very general overview of the quantum communication systems that one can have. So this is it from my side. If you guys have any question, then we can discuss. I would say not questions, but if you guys have any points to discuss, then we can discuss because I am still learning all these things as well.
Hello, sir.
Yeah, don't call me sir, just Harsh is fine.
Okay. So you discussed BB84 protocol now, and you say you are right due to this scheme is secure against eavesdropping due to no cloning theorem.
Yeah.
So what is this no cloning theorem?
Okay, so let me explain the network theorem. Okay. So no cloning theorem goes something like this. So assume that I have a classical bit, let's say some message, let's say hello, right? So if I, let's say, just copy paste it, copy and paste, so I can directly, copy paste this particular message as many times as I wish to do that. But in a quantum state, it's not possible, and that this is how it's not possible. So let's say I have a state psi equals to alpha 0 plus beta 1. Now, I don't know what the value of alpha and beta is. All I know is that mod square alpha plus mod square beta equals to 1. I know this thing, but from this thing, I cannot deduce what will be the value of alpha and what will be the value of beta. The only way for me to know the value of alpha and beta is to perform the measurement. Once I perform the measurement, then with probability alpha mod square, my psi will reduce to get 0, and with probability beta mod square, my psi will reduce to 1. Now, once I know this alpha, I can obviously know the beta, but then my state is changed from psi to 0 and psi to 1. So you see that initially I started with a state psi, but now as soon as I gain the information about the alpha and beta, my state is changed to either 0 or 1. So the original state, this is destroyed. It no longer remains the state. The quantum system has changed its state. So no cloning theorem basically says that if you have a state defined, like this, and this is the definition of state, alpha 0 plus beta 1, then I cannot prepare the other state with the same alpha 0 plus beta 1. Basically, I cannot copy paste any state.
Okay.
This is the basic idea of the no cloning theorem.
Okay. Thank you.
All right. If no one has anything to add, then we'll end this meeting over here. Just a reminder that tomorrow we have a session on quantum machine learning by Mr. Joy Shah, and we will start at the same time, 1:30 p.m. in the afternoon. And that particular session will be followed by a hands-on session on quantum machine learning. Tomorrow we'll also be giving out some information about the hackathon, how you can uh, form your teams and everything. So make sure you join that session as well. See you guys tomorrow, and thank you for joining today. Have a good day.